In this applet we will look at Hooke's law. Hooke's law will lead us into simple harmonic motion. We have here a spring that is neither stretched nor compressed. The end of the spring is at the 20 centimeter mark. All the units here are in centimeters. If we add a 100 gram mass onto the spring, it will settle down very quickly to an equilibrium position. That's because the friction is set to lots on the scale, whatever lots mean. It just means that with friction, this mass will eventually settle down to some value. That always happens in reality. There's always a certain amount of friction in the spring itself. The particles in the spring vibrate and heat up. The spring loses energy and settles down to some equilibrium position. If there was no friction, if I set the friction to none and attach this 100 gram mass and release it, what will happen is this mass will oscillate up and down indefinitely. This is the kind of motion that we will be studying. This type of motion is known as simple harmonic motion. Let's consider the forces acting on this 100 gram mass. We have the force of gravity, or the weight of the mass, which by Newton's second law is mass times acceleration due to gravity, or m times g, where g is 9.81 meters per second squared. The mass must be in kilograms. 100 grams is 100 over 1,000 kilograms, or 0.1 kilograms. Since this mass is in equilibrium, the resultant force on it is zero. So there must be an equal and opposite force to cancel this force here. An equal and opposite force points upwards, and its magnitude must also equal mg. So this force here is the force due to the spring, F sub s. It must be equal to 0.1 g. Now by Hooke's law, the magnitude of the spring force is equal to a constant called K, also known as the spring constant, depends on the material in the spring, multiplied by the extension of the spring from the spring's original position, which was at the 20 centimeter mark. So it's K multiplied by its new position minus 20. This extension is about 14 centimeters. Each of these units is meant to be 1 centimeter. Now 14 centimeters is 0.14 meters. It's 14 divided by 100. So 0.14 here. So you can see that from this equation we can actually work out what K is. K is 0.1 g divided by 0.14. This here is the force, spring force, so that it's measured in newtons, and we divide by the extension, which is in meters. So the spring constant has units of newtons per meter. So for this particular spring, K is 7 newtons per meter. Now here we see the 50 gram mass attached. What are the forces on the 50 gram mass? Well, we have its weight, which is only half of the weight of the previous mass. Its weight is mg, which is the mass in kilograms. That's 50 divided by 1,000 kilograms, which is 0.05. And because this mass is in equilibrium, we have an equal and opposite force acting upwards. That's the spring force, F sub s. That's also 0.05 g. And we know that that's equal to the spring constant K times the extension of the spring. Now the extension of this spring here is very nearly 7 centimeters, or 0.07 meters. So it's K times 0.07. So we could work K out for this, and we will get the same answer as before. So K is 0.05 g divided by 0.07, and that will come out to 7 newtons per meter, as before. So you can see that the force due to the spring depends on the extension of the spring. If we halve the extension of the spring, as we did here, by halving the mass, we halve the extension. We actually halve the spring force. If we were to do the opposite, if we were to double it, the spring force would be increased by 2. If we attach the 250 gram mass, the spring force will actually be multiplied by a factor of 5 when we go from 50 grams to 250 grams. So the extension of the spring is multiplied by a factor of 5. Knowing the spring constant K, we can work out the mass of this unknown mass. So the weight of this mass is mg. So that means that the spring force F sub s equals mg. They're the same because this mass is in equilibrium. But we also know that mg equals the spring constant K times the extension of the spring. I'll call it L. We can see that the spring is at roughly 42 centimeter mark. So we 42 minus 20, which is 22 centimeters. Divide that by 100 to get L equals 0.22 meters. We know what the spring constant K is from the previous examples. We know that it's equal to 7. So we have 7 times 0.22. So now we can calculate the mass. The mass is 7 times 0.22, which is 1.54, divided by G. Well, G is 9.8. I will use 9.81 for G, it's a bit more accurate. So the mass in kilograms is 0.156982, etc. To turn this into grams, we could multiply it by 1,000. So that mass is 157 grams to the nearest integer. Let's look at some qualitative features of simple harmonic motion. In later videos we will analyze simple harmonic motion quantitatively. Let's look at this 100 gram mass. It's in its equilibrium position at the 40 centimeter mark. If we remove this mass, the spring goes back to its original position, where it's neither compressed nor stretched. Let's consider the gravitational potential energy of this mass. The gravitational potential energy, written PE grav on this energy chart, is this dark blue bar. The gravitational potential energy depends on the height of this mass above some reference level. It's actually equal to mgh, where mg is the weight and h is the height of it above some level. We could take the height as being the height above the Earth's surface. So we could increase that height by raising this mass up. So you can see that that dark blue bar rises up. Or we could decrease the height by stretching the spring. So the dark blue bar decreases. We can also look at what's called the elastic potential energy. That's the potential energy due to the spring being stretched from its original position. So its original position was at this dotted line. So this light blue bar shows that we have some elastic potential energy in the spring, and we can increase that by stretching the spring. We can decrease that to 0 by returning the spring to its original position by raising this mass up. Now the elastic potential energy is 0. We can continue raising this mass up to compress the spring, which has the effect of increasing the elastic potential energy. Now let's consider the kinetic energy of this mass. To see the kinetic energy, we have to set this mass in motion. So what I will do is turn off friction here, so the friction is 0. This does not happen in reality, of course, but in future videos we're going to deal with this ideal case where friction is zero. It's easier to analyze the motion mathematically. Once we set this mass in motion, it will continue moving with simple harmonic motion indefinitely. So what I will do is I will give this mass, or the motion of this mass, an amplitude of 10 centimeters. I can do that by pulling the mass down to the 50 centimeter mark. So it's about here. So now it's the amplitude of its motion will be 10 centimeters. If I release this mass, it will oscillate indefinitely about its equilibrium position of 40 centimeters. So it'll oscillate between 30 and 50 centimeters indefinitely because friction is zero. We can see the kinetic energy going from zero to some max value over and over. The kinetic energy of a mass is a half mv squared. The kinetic energy is always positive. Mass is positive and v squared is always positive. So if we get the square of the speed, we have the kinetic energy. So when the kinetic energy is zero, it means the speed must be zero. In this case, the speed is zero when the mass is at the 30 centimeter mark or at the 50 centimeter mark. The speed is a maximum when the mass is at its equilibrium position of 40 centimeters. So this green bar reaches its maximum height when the mass passes through the 40 centimeter mark. Well, I shouldn't really say the mass, I should say the lowest end of the spring. To see that more clearly, we could show this motion in 1/4 time. So currently we're looking at it in real time. So now we can see how the kinetic energy varies with the position of this mass. Let's put it in 1/16 time. So here I have paused it at the 30 centimeter mark. At this mark, the speed is zero. When the speed is zero, the kinetic energy is zero. The potential energy is actually a maximum. Let's continue on the motion. When we reach the 40 centimeter mark, the kinetic energy is at a maximum. That means the speed is at a maximum. Now we won't really be discussing elastic potential energy here, but for now you can see that the three energies sum to some constant value. The total energy never changes. We won't be discussing thermal energy here either, but if I turn on friction, you can see it appear. So that's the red bar. So the particle quickly comes to a stop. Another thing that we can do here, which I won't spend much time on, is change the value of g. G is the acceleration due to gravity. So all along we have been working with a value of g for the Earth, which is 9.81 meters per second squared. But we could work with a smaller value of g. We could consider the Moon's gravity. On the Moon, the acceleration due to gravity is 1/6 of what it is on the Earth, 9.81 divided by 6. So that means that objects weigh 6 times less on the Moon than they do on the Earth. So we can change the weight of this object by selecting this here. So this object now weighs 6 times less. Let's go back to Earth. On Jupiter, the weight of an object is greater than it is on Earth. Jupiter is a much more massive planet than Earth. So its acceleration due to gravity is greater than 9.81. So this object would weigh more on Jupiter. So if I select Jupiter, you can see what happens. Now we have some other unknown planet here. If we select it, well, at least we can tell whether its acceleration due to gravity is less than Earth's or greater than Earth's by looking at the direction in which this mass moves. So if I select planet X, we can see the mass moves up, so its acceleration due to gravity must be less than what it is on Earth. This object weighs less on planet X than it does on Earth. Another thing we can look at is the situation where this mass is weightless. It will be weightless if it is well away from any mass, any planet, any star, any mass. We select G equals 0, it's weightless, so the spring is restored to its original position, its equilibrium position before a mass was added.